Okay, so before starting today, any questions from last class? Francis reviewed unit testing and debugging. So if you have any questions about that, let us know. Are good? Okay. There is a new assignment posted. If we have time, we are going to discuss it later today, but in principle combines the idea of using a repository, creating different versions, do a lot of commits, of course, and do some unit testing alone as you are committing the code. Okay. So today we are going to discuss something that is quite fun because it will bring us back to high school, I think, at the beginning, and then it will allow us to understand how computer actually deals with numbers. And this is quite important because at the end we are going to see what kind of things can go wrong because of that. Okay, so we are going to cover basically how we represent numbers, how the computer stores the different types of numbers, and then the different types or class of errors associated to that. So let's start by looking at how we actually represent numbers. And let's take this example, 1034, right? And we all know that we can actually split this number in the column of thousands, hundreds, tens, and ones. And if you want to explicitly mention that, well, you put the unit in front of each of these columns. For instance, 1 times 1000, 0 times 100, 3 times tens, and 4 times ones, right? So that's a very naive but clear way how we can actually represent this number. Now, what we are thinking about that, and another way to represent this is in powers of 10, because basically what we are using here is the decimal system, right? We are using digits that goes between 0 and 9, so the number before the base that we are using, and then powers of the base, power of 10s in this case, to represent the different columns. So 1000 I can write like 10 to the 3, 100 10 to the 2, 10 10 to the 1, and 1 like 10 to the 0. Okay, now nothing like groundbreaking concept here, but basically just to make contact with this. Now, nothing says that I can change actually the base that I use to represent this number, right? I could just change, and if you as I say, if you remember high school, you probably were told that we use 10 because we have 10 fingers, so that is easy to count, right? But we can change that number. We could change the base that we are using for representing the number, and let's say that instead of representing that number in base 10, I want to do it in base 7. Okay, so instead of having the 1000 columns, I don't know how I will call it, but it's 7 to the power 3, 7 squared, 7 1, and 7 to the power 0. And then I need to adjust the unit in front of each of the columns such that when I try to represent 1034 in decimal base, it gives me 3005 in septesimal base. Okay? Does this make sense for everyone? Yeah? Good. And of course, I mentioned this, depending on what base you use to represent the number, the digits in front of the column or the base goes between 0 and 1 digit less than the representation that the base of the representation are using. So from 0 to 6 in the case of the septesimal base. So now why this is important, why we are talking about this today, is because actually computers use a binary base. It uses zeros and ones. And the reason is because the original computers were based on transistors, and the states were on or off, as simple as that, or switches or lights if you wish. So the simple system that you can think of for representing numbers, for representing digits, quantities, is zeros and ones, a binary system. And that is what is underneath the computer representation of numbers. So 1034 that we learn how to represent in base 7 can be represented at this long number 100000000101 in binary base. And the logic is exactly the same. You have for each column the base, in this case 2 to the power of 0, 1, 2, 3, 4, and so on, until you fulfill the number, the quantity that you want to represent. Okay, so you can convince yourself that 1034 in decimal base is that long number in base 2 by looking at the power of the power of 2 and the coefficients in front of 2. Okay, and because it's binary base, I will have only digits 0 and 1. That's why actually we are using it. All right. Does this make sense for everyone? Any questions? No? All right. So I mentioned this. So the reason why we are looking at this is because modern computers still use this binary system. It's related to one way the simplicity of the binary system, but also the way that computers were created. Actually, if you look more carefully into assemble languages or compile languages, you will see that not only binary base is used, there is also hexadecimal base, which is based on 16. And you will notice that in some codes, in some assembler codes, or in some encrypted message that you get from the operating system, or when your code crashes or the debuggers, you will see digits going from 0 up to 9, and then from A up to F. And that completes 15 digits. So these are the 15 digits that you have in the hexadecimal base. And they switch from letters, from 9 to letters, because then there is no confusion if I'm representing a 1 and a 0 or a 1 and a 1 instead of 10 and 11. Anyhow, that's just an anecdote if you wish. So you can play that game and try to count also in binary base. Francis is very good doing that, so you can ask him to show how to do it. But let's go back to the problem of how we represent numbers in the computer, right? And on the one hand, we had this binary representation. On the other hand is how much memory, how much space can we take for representing numbers. And we are already familiar that there are different types of variables and different types of structures that we can use and have in C++, for instance, right? And the different types are associated somehow to the length, how much memory, how much portion of the memory I can take for store a value, being, for instance, a long integer, a small integer. And that is also related to another convention that the computer uses for representing numbers. So it's not only going to use binary base, but it's also going to allocate a fixed portion of the memory to represent that number. Okay. So in general, for integers, the good news is that integers, and this is one of the take-home messages today, the integers are precisely representable. Okay, because they are discrete, and I can increase by 1 unit, I can represent them exactly in the computer. Okay, and in general, like if you have a 32 bits computer, or 4 bytes, if you wish, a typical integer will have 32 slots, where one is associated to the sign, if it is a negative number or a positive number, and then the rest are just encodings, these zeros and 1 flags that I can turn on and turn off to represent the variety, the range of integers. So you can do the computation, and you can see that, of course, this is a finite range, but it will go from -2 to the 31 to 2 to the 31 minus 1, because we're including the 0, right? So if you look at that, there's that long number over there. If you are considered unsigned integers, meaning that you forget about the negative ones, then the range goes from 0 to 2 to the 32, of course minus 1 because of the 0 again, and this is more or less how it works. Now you will start to realize pretty quickly that these are limits. What happens if I had the number 2 to the 32 minus 1, and then I add 1 to that? Well, that will generate what is called an overflow. We're going to see examples of that. But again, 2 to the 32 may be a long number or a large number, but it may happen that because of the computation that you are doing, the calculation that you are doing, you may go over limits, beyond those limits, and you need to be aware of that. Okay? Any questions about this? We are going to see. So, all right. So in the same way as having integers, we have long integers. So if for whatever reason you are in those cases where you run out of range, so you are close to the range and you need to keep increasing your numbers, you can use long int, and we're going to see also how to define them in C++. The limits are way larger, minus 2 to the 63 up to 2 to the 63 minus 1. You have the digits there, don't ask me to read that. Or if you are using unsigned long integers, and actually that's the reason why many languages allow you to define unsigned objects, unsigned type of variables, is because then you have a larger range, right? And again, the construction, the structure of these objects, of this type of variables are the same. 1 bit for the sign, and then the 63 remaining for storing the zeros and 1 in powers of 2 to get the representation. Yep. You get what is called an underflow, which is like wrapping around. We are going to see examples of that, but yes. Any other questions? No? No, cool. So this is a summary of the types that you will find in C++, at least for the integer types. So we have just 1 byte just as a reference there. We have short integers of 2 bytes. We have integers that it may be 2 or 4 bytes depending on the architecture. We have long integers that is 4 bytes, or long, very, very long integers with 8 bytes. Okay, and that's are available in the C99 and C++11 standard. So here on the right are different ways that I can define. Some of them we may have seen, some of them we may have not seen, like the unsigned ones, and you saw that it's mostly for extending the range, but only considering positive values. But yeah, so this is a different ways that you can define the same kind of objects or variables, depending what range are you interested in considering. The ranges are described here. We have some of this in the previous slides, but basically it's the computation I showed you. If you want to know how many numbers you can represent for integers, you just take the bytes or the bits and you elevate to the power of 2 and subtract 1 for considering the 0 element, the null element, and that's it. Okay. Overflow. So you guys were asking about overflows, and this is actually 2 examples. The first one, I'm actually using an unsigned short integer, and I'm actually giving the largest value possible. Yep. I don't think there is any difference at all. I just here, you mean? It's the same. There is no difference. It's just 2 different ways. Yeah, I think that the same way that you have different ways that you can initialize variables or arrays, these are like different ways. In some cases, it may be cleaner or clearer for you, but in principle, regarding the variable itself is the same. Overflow. So in this example, I define a short integer unsigned, so from 0 to 2 to the 32 minus 1, and I'm giving actually the 2 to the 32 minus 1 value there. And the next thing is I'm going to print out what is the value. I'm going to add 1 and print again which is the value. Very simple example. I compile this thing, run it, and you get that actually what happened is that after getting the maximum came back to 0. So it's basically circular, the representation that you have. And this is the concept, the very basic concept of overflow. Similarly, I think you were asking about this. If you have 0 and you subtract 1, it wraps around by the other end. So you get 0 and then the latest or the largest option. Okay. So these are the things that one has to be aware. That is the reason why we are discussing about this today. Is like usually people, especially if you come from the camp of using Python or R, you may not be aware because many of the things are hidden behind the interpreter or how it's implemented underneath. But when you are doing coding in C++ or Fortran in particular, these things can bite you, and you need to be aware of that. And things you will see, they are going to get a bit more hairy when we are doing we are going to deal with real numbers and the floating point representation. Just a one slide here. This is not too common to find, especially in scientific computing. It's more common to find in other fields like economics or stock markets or something like that. There is this representation which is called fixed point representation, and basically keeps the decimal point fixed, and you have a certain number of characters or digits that you can use for representation. We are not going to discuss this much because, as I say, it's just for letting you know that this representation exists, but it's not the most common one that is used. And it's, of course, for representing real numbers, if you wish, and not just integers. The one that we are going to spend some time talking about, though, is the floating point representation. And this one is very common and very well known in the scientific community, in engineering. And basically it's composed by these following elements. So you have a sign as before, you have what is called the mantissa, you have the base of the number that you want to represent, and the exponent, right? And what we usually do is we move this decimal point accordingly to the power of the exponent that we choose. So if I want to represent like always one digit leading here, I always adjust the exponent such that whatever comes after is the decimal positions, or even if I want to represent a million, I can say 1 point something times 10 to the 6 or something like that. Okay? So that is what we usually do in scientific representation, for instance. In the computer, this has to be mapped, right? And again, the computer is going to represent in this kind of linear structure in the memory. So 1 bit goes for the sign again. In research, in general, 8 bits for the exponent, and then the remaining 23 bits are for the mantissa, which is this number here. Okay? Yep. The example I'm writing here is base 10. The numbers that are going to be located here in the structure are going to be base 2. So underneath in the computer is still base 2. The exponent is for base 10, but the representation here again is going to be binary.
That's
just yeah.
Yeah, all base 2. Actual stuff.
Remember that slide at the very beginning that we had 1034, and then I have the columns multiplied by 10 to the something, and then I have another expression like 1000, and I have the 2 to the power of 7, 8, or something. So these are the powers, the exponents of those columns. So I thought this is easier to see this because we are familiar with that, and to identify how we call, but at the end, these are all powers 2.
7 powers of 2. So, either in a sense, we write.
We lost.
7.
Yeah.
And then that minus 7.
Okay. What happened with the whiteboard? We lost it. Like. It's gone. Okay. Okay. So let me go back and try to make the example. So that is the one to. Yeah. This is 1034, right? So it will be better slide. So this will be the representation that you will get. It will be 1.000000101 times 10 times 2 to the power of 10. That will be the representation in the floating number representation in that interpretation. So you take the highest power of the base 2, you represent that exponent in the exponent, and whatever came after, which is the mantissa, goes in the other part. Yep.
This binary, this number is assumed. Again,
inside the memory is always going to be, the exponent is going to be the exponent of a base 2, and the mantissa is going to be whatever comes after getting that number, right? So in this case, is if I want to represent this number in base 2, but in floating point representation, it will be 1 point, and then whatever comes after, and then all times 2 to the power of 10. So it's like having a decimal point for the binary representation. Here is an example can be. Yeah. So let's take the 134 that we have right there. One way to represent is to put sometimes this angle shape there in base 2. So this was something like 1, 0, 0, 0, 0. I may be missing a couple of zeros there. So that is in binary. But this in floating point, I could represent like 0, 0, 0, 0, 1, 0, 1 times 2 to the power of 10. I'm missing one? Oh, sorry, yeah. 1, 2, 3, 6, 7, 8. There you go. I think I don't miss anything. 2, 3, 6.
And you store still all those numbers.
So it's like saying like another way to think about this. This can go like 1 times 34 times 10 to the 3. So I'm basically adjusting the exponent such that there is only one decimal point or 1 digit before the decimal point. Yeah. So that's the whole trick, right? So you can see that there is a bit more of gymnastics in the representation of the floating point numbers because of this leading digit there that it has always, or is always good to have like different from 0 at least, right? So if it were 0.34, it will be 3.4 times 10 to the minus 6. Just to give you an idea of the ranges and the types, so you can have floats, doubles, or long doubles. And the numbers associated with that are 4 bytes, 8 bytes, or 12 or 16. Again, this may depend a bit on the architecture that we are talking about. But still, it's a long range of numbers that you can still represent. So, and it goes, interesting thing here now is that it not only goes from positive to negatives, but also it has some certain resolution, if you wish, of which is the lowest values that you can achieve to represent in a machine, because now we can give also sign to the exponent, and if it is the value is negative, we are getting values close to 0. So in this case, 4 bytes will give you up to 10 to the minus 38. 8 bytes will give you 10 to the minus 308. 12 bytes and 16 bytes will be you something close to 10 to the minus 5,000. Not exactly 5,000, but 4,951 or 4,932, something like that. Okay. Similarly, you can go to very high values in the exponent and high values in the representation. Okay. Again, different ways to define these types, different ways to initialize as well. And also, we're going to be talking a bit more about precision. Okay. So there are some special numbers or special representation, if you wish. This is mostly based in IEEE standard 754. But the problem happens when you want to represent infinities. That can result as any kind of mathematical operation, like dividing over 0, taking the square root of a negative number, those kind of things. Another thing that you will start to notice is, and probably you have noticed if you have been running any kind of code that does some computation, is to have sign zeros. So you will may have a 0 plus or positive. Of course, the nonce, which can be a result of also divisions by 0 or divisions between infinities. So all these things have to be taken into consideration. Again, this is not Python, not R, that you can set some flags and ask the interpreter to take care of that. As a programmer, you have the whole control of the situation, so you need to be aware of this and take full responsibility for saying somehow of these cases. Okay. Someone was asking about how we can detect and about how to get the limit So there is in the numeric limits interface with C, it's some sort of class and template. So you can get all the limits for the different types of variables that you are going to define by using the template. And you have some member functions associated, which are quite useful actually. So you can get which is the minimum, the lowest, maximum. We are going to be talking about this guy, the machine epsilon, which is the smallest quantity that you will be able to represent. You can get infinities, nonce, signaling nonce, different kind of signals that will allow you to have more control and know what is going on with your computations. Okay. Okay, let's take a look at how to use this. So let's say that I want to get the limits for integers, lowest and maximum, and I want to get limits for floats, lowest and maximum, and I want to get the limits for doubles. So it's as easy as calling the limits header, and then basically from the standard use numeric limits and the type. So this is what I think we mentioned this before. This is kind of template functions that you can just, it's always the same function, but you specify the type and you get the member function associated with that particular type. Okay. So compile, run, and basically you get your limits there, and you can try to see it probably matches quite accurate the description that we give in the previous tables. Okay, so you can have an idea of those limits if you don't have a table handy by using these template functions. Okay. Yep.
Kind of function. Say side brackets are why do people think
For the types, you mean?
yeah, I was just wondering because I mean only make I don't know it's like
Right. Well, on the one hand, what you can think of is the power of that function, right? So you are basically writing a function that takes any type of variables and returns you something. This is one of, I think, what I found one of the most illuminating cases, because all this type has some limits associated, but it changed depending on the type, right? So the type for the limits for the type integer is not the same as the float or double, and these kind of functions can actually help you that. I mean, writing templates or programming in templates is something that is people have been doing for a while, and it has some strengths, especially when you want to do something agnostic in the sense that I don't care the type, but I want a result, or there is a result associated to each type, which is different. That's the I think one of the strengths of template programming. There are other tricks that you can play, like do pre-compilation or put things on the fly that the compiler will take and do something while it's compiling. So some people, I know some people use this kind of programming for actually doing computations during the compilation, but this is a completely different thing. Because I talk about limits and I talk about the standards, I should mention that there are these two standards, and depending if you are using the 754 or the 854, this is getting a bit technical, but just to let you know, depending on this standard, the float on the double will have these numbers. And we talk about this. This is basically the mantissa, exponent, and sign representation. So again, these are the range of values that you may expect to have for floats or doubles. Okay. So it's almost twice for a double. At some point, many years ago, people even don't have these implementations on the standards. So you have to, if you want to use double precision or quadruple precision, you have to use particular libraries. But nowadays, they are part of the standard. So that's for the exponent. No, basically I see what you mean. So the negative there is encoded in the exponent's bytes itself. So it has, I don't remember if there is the first bit. Yeah, there's this.
by
Yeah, there is. Yeah.
So essentially, of course.
Yeah. So it's instead instead of starting in series, you start in this offset. It's kind of an offset. Yeah. Why is the machine epsilon so much bigger than the smallest number? That's a great question. So this is the smallest number that you can represent, but doesn't mean that you can jump between these numbers by just, so the smallest representation doesn't necessarily fit the smallest jump that you can have between numbers. So it's kind of measuring the granularity between the numbers. So we're going to talk a bit more about the machine epsilon, but you can see that that changed a lot depending if you are using the float or the double, right?
Essence, you have but because I have component multiplied by all real, I say this.
Yeah. Right. Any other questions? So talking about this IEEE, you can check if you have in your system these libraries. If not, you can install. If you're using Linux, you can just do locate and the header file, and you can include the library. And then we're going to see actually how to compare numbers, in particular with floating point. This is not necessarily the best way to do it, but you can use all this information, in particular from the IEEE. So at the end, it's kind of very similar to using the limits template library, but just provided by this standard. So engineers pay a lot of attention to this. So if you're doing computations with engineering, they are going to probably ask you to use one of these standards, either 754 or 854. Okay, so why we are talking about all of this again? You can start to have the feeling that some things are not as precise as one may think. And of course, as errors may crawl in your integer computations, more easily will crawl in the floating point computations. If these errors or this lack of precision, if you wish, are important or not, at the end it may depend a lot on your computation, on the precision and accuracy that you need to achieve. But let's take, for instance, the case where we have floats and doubles, different values, 0.01 and 110 to the minus 17. I created a function here, output, that takes these two and basically prints them and print different operations between them. Okay. I don't think I have the output here. I encourage you to try this. It's easy code to code and see which are the results. Some of them will surprise you. Okay. The other thing that you may want to be aware, and I think someone was asking this for the first assignment when you had to generate this Lisa shoes pattern, you can control the precision. This is not necessarily related to the representation, but yes, on how you save your data. We're going to talk more about saving data, in particular into files, into text or ASCII and binary formats. I'm just letting you know in advance, binary is always preferable over text or ASCII, because on the one hand, you can save the data as precise as the computer has the representation, and it's faster because there is some conversion involved when you are saving text. But in any case, what I want to emphasize is that you can control the number of digits that you want to output by setting the precision in the output that you are generating. So the other thing that we may want to think is how we represent fractions or how we represent rational numbers. So 1/3, we know that is 0.3333 and continues like that, right? So which is the right representation and which is the representation the computer is going to take? Of course, it's going to be limited by these ranges that we are talking about. But what is related to that is when you have these cases, you end up with something called unit in last place error. And it's basically an error that you had in the last digit that you are using for representing these fractional numbers. What is the problem with that? Well, in principle, it's not much of a problem, but the representation per se, because if you are aware of that, it's like measuring some data, right? You know that there is an error. The problem comes when this starts to be part of following operations, and that's why this example here. And this is just adding, dividing. It's a very simple example. Imagine that you have more complicated operations. These problems or these errors are start to going to propagate. And if you want to actually achieve the end result and know which is the error, you will have to do something like error propagation method or something like that. Okay. This is another example. In base 2, you want to represent 0.1, just 10 to the minus 1, very simple number. You will get a basically infinite sequence of zeros and 1 to represent that. Okay. The other thing that we should mention is what single and double precision means, and it means taking one part into 2, because now we know that the representation is binary, 2 to the number of digits that we are going to use, or bytes. So in this case, single precision is 6 times 10 to the minus 8, or 1 times 10 to the minus 16 in case of double. And these are the numbers that, if you recall, are kind of what we call machine epsilon. But that is what we're going to discuss. Okay. I mentioned this, and in the previous example, I have A double equal B, which was asking for is A equal to B. And one of the other messages that you probably want to take home from today's lecture is never, ever check for equalities just by looking at the two numbers. We have to check for equalities because these round-off errors or this inaccuracy in the representation by asking of a given tolerance if these two numbers are equal or not. And usually this tolerance is something that you set, but it's something that is also related to the representation, meaning if it is a float or a double, and also on the compute. So in this example, I have, again, a float, two floats actually, f that is 0.1, and then g, which is the square of that. So the program is going to print that. It's going to ask, is f squared equal to g? Very, very naive question, if you wish, right? Because we just compute g being f squared. And if print true or false. Then I'm going to set something, a tolerance, which is of the order 10 to the minus 15 in this case. And I'm going to ask, is the absolute value, so from the C math library, if the absolute value of f squared minus g is less than that tolerance. And ask if it is true to print true or false otherwise. Okay? So you compile that, you run it. And what you get is that when you are asking for testing the quality between the two variables itself, it's not exactly the same. But when you ask for the tolerance, then you get the result that you may expect. Okay? Yep. If you check the representation, if I have different variables with the value 0.1, if this is what you're asking, that representation should be the same. Approximately 0.1 is also one of these peculiar cases because if you saw before, it has an infinite representation. But in principle, in theory, let's say it will. The problem is when you start to do the computation, right? So because of this infinite precision, now there is an operation involved. It's a simple multiplication, but because we have the infinite numbers representing that, now you will lose some digits in the representation. I will expect to get the same, but the right way to do it, if you ask me that, is actually to always test for this. In paper, if we do the analogy of writing this in base 2, representing, cutting the limits according to the bytes that we have for representation, in paper it should work. But I will suggest always to do comparisons this way. Okay. One thing that you will notice though, and I think this I mentioned, integers are safe from this illness. Okay, because internet has a precise representation. It's only when we reach the word of the floating points numbers when we are facing this kind of problem. Yes, we are going to see that in a second. This is another kind of errors that you may find with floating point representations, just changing, commuting the order of operations, something that in our classic algebra shouldn't happen. This is a very simple, naive also, but representative example of what I'm talking. So A is 1, B is 1, C, which is related to the value of epsilon, is 10 to the minus 16. So I first subtract A and B, and then I add C. Okay, and now I change the order. I subtract B from C, and then I add A. So same mathematical operation, different way to do the operations, or different order in which performs the operations. And in one case, you get what you expect because the ones cancel out, which is 10 to the minus 16. In the other case, you get something else than 1 10 to the minus 16. You can certainly claim this is tiny, but the results are different. And again, if this is part of a bigger computation, you will start to see these things crawling in, right? What is happening here is these numbers cancel out fine, so you just add that. This number, which is minus 1, is way, way far away from the 10 to the minus 16. So the computer will have to somehow figure out a way to keep that information both in the same allocation. Okay. So this all is related to this machine epsilon, which, if you wish, the formal definition is the upper bound of the relative error due to this rounding. For floating point, for single precision is 10 to the minus 18. Sorry, 8. For double precision is 10 to the minus 16. It's twice basically, or power 2. These kind of errors you may find again in simple operations like subtracting or dividing. Again, this doesn't happen to integers. So the problem is when you are actually forcing the computer either to deal with these numbers close to the limit of the machine epsilon, or when you are asking the computer to deal with numbers that are too far away in the representation. Like one is several orders of magnitudes different from the other. Just to explain, this is the same example as before. If I'm adding 1 and then 0.001, 10 to the minus 3 if you wish, you can see that I'm losing one digit in the representation. Let's assume that in this case we had a exponent precision of 2 and a mantissa precision of 3. So I can keep 3 digits, right? So this is a 1, this is 0.001 or 10 to the minus 3. So if I have to put all the numbers, my 1 is represented with 4 digits in the mantissa. And this guy I had to lose. I don't have enough room to accommodate that. And that's why 1 plus 10 to the minus 3 for the computer in this case is going to be 1. Okay, so it's due basically to the limited resources that we have for representing number or slots in the representation. Okay. So let's go back to the machine epsilon and let's see how we can actually get a number. And there are different ways. You can implement an algorithm for getting that. We have even in the past had problems asking you to implement an algorithm for determining which was your machine epsilon. Or you can use some library functions, of course. So coming back to definition, the machine epsilon is the x such that when you add x to 1, that is different from 1. And the small n x possible that is possible to represent. Or sometimes the opposite. It's the largest x such that when you add that thing to 1 is equal to 1. Definition is up to you. So in this case, let's take a look. So again, I'm having floats, and one is 1, the other is 10 to the minus 18, just for giving a number. So if I do this very basic operation, subtract 1 from 1, and then add this number, what I will expect, and invert the operation as we did before, and play around with that. So in those cases, you will see, okay, f is 10, g is 10 to the minus 18. So in this case, as before, we get 10 to the minus 17. If we do this and subtract, then we get 10 to the minus 18. If we add 1 plus 10 to the minus 18, we still get 1. So that means we are below our machine epsilon. How we get that value from the computer? Well, this is an algorithm that can do that for you. So we define a function called half, and basically takes the argument, add 1, divides the argument over 2 and add 1, and asks, is this greater than 1? If it is not, then computes half again. If it finds that it is, then it returns that value. Okay. By the way, this technique of calling the function itself is something quite powerful. It's called recursivity. I don't think that we are going to see much of it, but it's something that you should be aware. Many mathematical operations are quite suitable for this technique. Factorial, think about factorials. If you want to compute a factorial, you can call once and once again the same function, and at the end you will get the result. It's very, very elegant from the programming point of view, and it has some other perks associated. So if I do that, I run this program, I get that my halving is around 10 to the minus 16, which is kind of what I was expecting. Additionally, I can use the numeric limits, as we mentioned before, and ask for epsilon, and that will give me, so I got epsilon up to a factor of 2. That's probably the way the way I was doing the computation, the division. But this is, at least you get the right order. Okay. Alternatively, you can use again the numeric limits for get the epsilon for different types. So notice that the machine epsilon, which is consistent with what we were saying, the integral representation is precise. There is no loss there. Is 0. The floating epsilon is 10 to the minus 7. Double is 10 to the minus 16. Okay, so there are different tools you can use or implement if you want to know which is the machine epsilon. Okay. Any questions? Okay. So this is another example of how to be aware of or how these things can crawl in your computations. And in this case, I'm going to have a list of numbers, 200 numbers, that I want to compute the square root of the number. So I'm going to take x, basically is dividing an interval between 0 and 1 with 100 representation, and then compute the square root, and then ask the same question as we asked before, is the square of the square root equal to the number? Okay. And then I'm going to save this in a file, and I'm going to plot that. Okay. So what will happen is, if you do that, this is what will happen. This sky blue cyan line is actually what the square root should look like. So if I take the number, I compute the square root, this is what I should get. The purple crosses or line is the values I'm getting. And what you can see is if the number is below 1, the square root is being pushed to 0 basically. And if it is above 1, it's being pushed to 1. So this is due to what is coming in the argument of the square root. Yep.
Perfect. Any times?
No, it's just 2 times I think. Oh, sorry. It's just yeah, it's like 200 times. That's right. I'm taking the square root 200 times. That's right. Still, if everything goes well, you should recover the same number that you started. So there should be this straight line, right? That's basically what I'm trying to show. So this is called catastrophic cancellation. So it's successive applications of one function, or can be different functions, that you are losing precision. So it comes back to this issue that of having the finite size mantissa and losing this last precision number. And at the end, you will run out of precision, you will run out of digits, and your number get pushed to the closest integer somehow. Okay, because that representation is not. An example of overflow with floating points. We saw overflows with integers. Same thing can happen with overflow with floating points. So if you go beyond those limits, the representation start to wrap around. So it's circular representation again. Sometimes it's very tricky because if you go several times over the range of the representation, you don't know if you are overflowing or underflowing, and which direction you are circulating. So again, this is another. So and you can see these examples are quite simple. It's just you get a particular value either close or far away from the limits, and then you start to see these things. And in this case, you can see, well, there is an infinity, so you know for sure something went wrong there. Okay. Similarly, underflow, and I have been using overflow and underflow indistinctly, but people is more picky about that. And underflow is when you actually down in the minimum or precise representation. So if your number goes below the machine epsilon, basically you are underflowing because you cannot represent that quantity, sort of. Okay. So in that case, I have very tiny numbers. And again, you will see that things mostly happen when there are a huge range of digits or in the representation. So something negative 10 to the 35, 44, and then something of order 1 to the minus 44 or 46. Just printing those things, and you will see that many of those are giving you infinites, negative infinites, or just pure zeros. Okay, so in this case, it's something that is falling under the granularity of the representation, if you wish. There is one more type of error which I'm not going to cover today because we're going to have a whole lecture about this or related to this, but I just wanted to let you know about this. Is what is called discretization errors. And these errors are, so the difference with the previous errors are those errors are intrinsic to the representation per se of the numbers. These errors are related to that, but it doesn't come because of the representation of the number per se, but it comes because of the representation of our mental model of the problem. What I'm trying to say is, if you want to solve a differential equation or do some sort of integration, any kind of computation, we certainly don't have continuous fields in the computer. We have to discretize that. So if I want to compute the derivative, I need to do a delta instead, a difference, right? So whatever is the value of one field in this point minus the value of this field in the other point divided by the length of the integral. That's how I will represent a derivative in the computer. Similarly, if I want to integrate, right? So this is called discretization errors, and I'm associated from when I take something that is continuum, and then I have to discretize because that's the only way I can handle it in the computer. So when we do that kind of things, you can very quickly imagine that many errors start to crawl in again here, and are associated to that discretization, but also tied to the representation of the numbers.
Assume a difference. Assume that you're solving a differential equation for.
If you, yes, that's right. But if your equation is a differential equation in nature, then there is some error associated with that. But yeah, so if your equation is in differences, that is it. You still have the other. You still have to consider the other kind of errors that crawl in because of the representation of the number. But yeah, that's correct. So yes, that's that kind. So that's why it's called discretization errors. It only happens when you discretize. If your equation is discrete, okay, you are proof of that. Okay. So we are going to repeat this, and there is some interesting concept here. So don't worry about this. We are going to pass this and come back to this when we do the differential equation class. So for summarizing today, the things that you need to remember is, okay, integers are stored exactly. Still, they have limits, ranges. Floaters point in general, unless that you have a very particular case, are in general not stored exactly, and so rounding errors will appear in the representation. Again, my suggestion, I strongly advise you to do that, because then you will find yourself scratching your head, like looking at your code for several weeks. Try always to test equality with a cutoff or a tolerance factor, instead of just looking at the two variables. This is especially true for floating point. Be aware of the epsilon machine. So, yep. I don't. Let me think. I don't think the inequalities is as complicated as looking for the quality. They are more complicated.
Because think of case around the other way around.
Yeah.
So now you have part of that absolute. Because from absolute A minus, I don't know what you're. Yeah.
There are some tricks that you can do, though. Yeah. Yeah, there are some tricks that you can do, like you try to maximize the difference somehow, do some operation like taking squares or logs if they are positive numbers. So that may maximize the difference. Yeah, no, that's right. Many of the things are related to the precision and accuracy, which in principle are two different concepts, but at some point they go all together with the machine epsilon. So this is kind of the tipping point there. Errors like this catastrophic cancellation, which is related to the maximum or the final representation, can be like sometimes the cause of this other type of errors. And again, overflow and underflows again cause of the final representation. Okay. The discretization errors, we will come back to them when we do the differential equations. Any other questions? Let me just flash for you the assignment. Have an idea of what we are talking about. So it's related to testing and version control issue. So first step, and this one you had to do only once, is you had already Git in your computer and you're ready to go. But if not, you will have to install it. In the slides, there are different options how you can install it depending on what operating system you are using. Second step is to create a local repository, and I will advise you to do is to create your own directory for each of the assignments, and then because this is going to stick with us for the rest of the course. So every time that we have an assignment, we are going to ask you to create a Git repository. So my suggestion is every time you have an assignment, create a folder, assignment 1, assignment 2, well, not 1, but assignment 3, 4, and so on. And in each of them, you create the repository. We're going to be using the previous code that you already modularized. So grab that code, commit the code, and then there are a sequence of steps. Some of them you had already done, like comparing the solution or the results from the original code and the modularized code. But now you will have to implement that in the main file. So there should be a rule now that is called integrated testing or something like that. I think integrate test. No, there's another one before, right? No, that's the one. So that's the first one. Yeah. So integrate test, I will actually compare for that. Then you're asked to create a test in particular for the evolution module of the code. And what we are suggesting, because it's the easiest one, I think, is to give initial condition at this all 0. So the evolution code should produce, or the evolution module should produce something that remains 0. So that doesn't change. Right? Create another rule for that, make unit tests in this case, perform this test, and the other thing, the last part, is to change the dynamically allocated arrays by the RArrays library. You need to download and install the RArrays. Just clone. It is git clone there, so you can git clone that repository. Change that. Do the different tests with the RArray implementation. Be sure that everything is working. And in every step, I will suggest, plus more, do commits. So initially, I think we expect at least 5 to 6 commits minimum. So any questions about this? I don't know if you had a chance to read it, but it's a code that you guys already kind of know. You have been working on it. And the other thing is, when you submit the files, also include your git log. So use git log --stats. --stats give you much more detail of what had changed in each of the commits, which files had changed. So it shows you the log. I think we saw the log, the author, the time, but also will tell you which of the files has changed and what modifications each file has. Okay. All right.